what we were doing related to the theoretical aspect behind what we are doing right now. So remember, what we have discussed so far is that we have a signal in time domain, x of t, and we can actually also, so this signal would look like this, okay, so just a function of time. Okay. And we also sometimes want to look at this signal in the frequency domain, and in that case it's going to be values versus omega, the frequency. Maybe it will look like this, okay, whatever. Okay. And there is a mathematical process that allows you to look at the frequency components of the signal, amplitude versus different frequencies, and the time domain representation of the signal, amplitude at different time instances, which is like the natural way we learn how to deal with signals. So the time domain is the thing that you have been learning since your early math days, a function of time or a function of a variable, and then most of the signals that we deal with as human beings, we treat them versus time. However, we will see today, after doing some theoretical stuff, that without really going also to the frequency domain, there are some operations that we might want to do. We might want to process a signal in a particular way. And if we try to look at these operations in time domain, it doesn't make sense to us at all. We will not be able to really understand what are we doing to that signal. But once we start looking at the signal from a frequency domain perspective, we will start understanding, oh, we are actually doing this or doing that. And we will see that a little bit later, okay? So going from time domain to frequency domain in this direction, we perform what's called the Fourier transform. Coming in the opposite direction, we perform what's called the inverse Fourier transform. And the two processes looks very analogous to each other, or whatever. I don't know how to pronounce that word, but there is an analogy between them that's easier to pronounce, okay? So what was the mathematical function? If I have the frequency domain and I want to get the time domain, then the equation was, if I have the time domain and I want to get the frequency domain, then the equation was that this frequency domain representation is the integration from minus infinity to infinity, my time domain signal multiplied by e to the minus j omega t, and I integrate with respect to time to get a function in frequency, right? And that's like the forward way or the Fourier transform direction. The other way is if I have the frequency domain and I want to deduce from that what was the time domain signal, I do the inverse, and that one is calculated as 1 over 2 pi, the integral from minus infinity to infinity, frequency domain signal multiplied by e to the j omega t, and this time I integrate with respect to frequency so that I can get a time domain function or signal, okay? So these two processes, they look very similar, right? So e to the j, the signal multiplied and integrated, the signal multiplied and integrated, the integration from minus infinity to infinity is only just plus and a minus sign here, and just a scaling factor here. Okay? So the two operations are very similar to each other. And we'll see that this similarity is helpful to solve some issues as we'll come to this later. Okay. Now, this mathematical operation is exactly what you tried to do with MATLAB. Basically this one, when you recorded your voice as a time domain signal, and then you try to look at the Fourier domain representation or the frequency domain representation by doing the function FFT in MATLAB and then adjusting the scale and the stuff that you needed to do in order to get eventually x of omega. So you just wanted to look at the signal as a function of frequencies, different frequencies, to see how much frequency it spans and so on, okay? There are some important functions that we will try to address today, and they happen repeatedly, and we need to know how to figure out their counter frequency domain representation. Those functions are, and I assume there is a question that might rise in your mind as soon as I show you the functions. Let's see. So those functions are the rectangular pulse function that comes from minus t over 2 up to t over 2 and has a height equal to 1, or any general height, but we will do it for the case of height equal to 1. Let's call this x1 of t, first one. The second one is the shifted delta function, or any delta function in general. So as a function of time, we are looking at delta of t minus t naught. Okay, let's call this x2 of t. And then the last but not least is a phase factor. Okay, so as a function of time, plotting this one is not easy. So let's skip plotting it. Let's just write it down, because it's a complex number function, so it needs to be plotted as a magnitude and a phase. Okay, it can be plotted, but let's skip the plotting now. So it's e to the j omega naught t. So generally, e to the j some constant multiplied by t. I call it omega naught for a particular reason, this constant, but it can be anything. I mean, I'm not saying it's a frequency, but calling it this way would enable us to understand how it looks in frequency domain. So it can be e to the j 80, e to the j 3t, whatever, okay? So that's just a pure phase term, because in terms of a magnitude, this function has a magnitude equal to 1 across any time, right? But in terms of a phase, it's a linear phase term. So the phase of that function is going to be a linear function with respect to time, okay? So each one of those, we need to know how it looks like in frequency domain. The question that might come to mind for you is, well, what we have been doing right now, until now in the project, has been actually dealing with some general function that looks like x of t that we see up there, which was the voice recording. And then we looked at it in frequency domain, and it doesn't seem that I can record my voice or get some signal from the natural world that looks like this square function or a delta, right? They seem like very theoretical, so why they are relevant? And the relevance of those functions comes from the fact that they are used by different systems. So later on, when you want to process a time domain signal or your voice or an image or whatever time domain signal, and you want to process that to produce something like the equalizer that we are dealing with right now, you will encounter systems that has this type of a function, or this type, a delta function, or even a phase shift, okay? So these are particularly important, not as being actual signals, but as being some functions that will be applied to signals in order to produce a desired effect, okay? So mainly these will appear in systems rather than in signals. So again, if they appear in systems, why do we care at looking at about looking at them in the frequency domain? Because again, if you convert a signal to the frequency domain representation, if you look at it from a frequency domain representation, and now you want to process it through a particular system, it's much better that you also convert your system response into frequency domain and then start doing the processing operation to get the output that you want to receive. So if we have systems with such functions, we need to know how they look like in frequency domain. And it just happens that many of the common operations that we perform in systems, they use variations of these functions. So that's why we care that much about these functions, in addition to being a nice introductory part to see how we calculate the Fourier transform for different signals using the definition itself. So for those functions, in order to calculate what's the frequency domain representation, those are time domain functions, right? What's the frequency domain representation? You will need to just apply them directly into the definition of the Fourier transform, okay? So let's try to do this one at a time. So go to the next slide, and then we start by x1 of t, which simply looked like this. Okay, so it was, and t over 2 here, minus t over 2, a value equal to 1, as a function of time. And by the way, if typically this function is written as rectangle of t over the width. Right? So this is how it's written. Rectangular function as a function of time, and you have the time variable t divided by the width, which means that if t is equal to 1, this is rectangular of t. If t is equal to 2, you know that when you divide the time variable by a factor, it means it's a wider signal, right? So if t equals to 2, it means it's a signal with width equal to 2. T equals 3, so it's t over 3, which means that it's a signal with width equal 3, and so on. And then again, if you have an amplitude to that, then it's multiplied by the rectangular function. And if you have a shift, then you can introduce that as a time shift. If it's not centered around the y-axis, then you will have rectangular of t minus something, right? Okay, so you can play with this signal to represent this rectangular or this pulse function, both with varying the width, varying the height, and moving it to the left or to the right as you wish. But for us, we will focus on the basic one that we see right here. Okay. Now, if you want to calculate the frequency domain representation, you only can opt for using the equation. So x, let's call it x1 of omega, is equal to the Fourier transform of that signal, x1 of t, which is simply defined as the integration from minus infinity to infinity of the function x1 of t e to the minus j omega t, and you integrate with respect to time. Now substitute the x1 of t. x1 of t, when you look at it, is equal to 1 only from minus t over 2 to t over 2, and it's 0 everywhere else. So we only need to integrate from minus t over 2 to t over 2, and the value of the function in that range is going to be just 1, right? So this integral becomes the integration from minus t over 2 to t over 2. The value of the function is 1, and then we have e to the minus j omega t dt. Can we solve this integral? Yes, we can. So minus 1 over j omega multiplied by e to the minus j omega t, and substitute the upper limit, substitute the lower limit, right? Then can be written as, I'll just play a little game here. So I'll keep the 1 over omega by itself. I'll multiply up and down by 2. So I have 2 over 2j, okay? And then the substitution, I'm gonna flip so that I get rid of the minus sign. So I will have the e to the j omega t first, and then minus the e to the minus j, omega t, capital T over 2 first, and then minus the e to the minus j omega t over 2 second. Okay. Now, why did I do this? Separate exactly. Separate the omega, multiply by 2, and then get a 2 here, because I want to use 1 over 2j e to something, j something, minus e to the minus j something. It means this whole thing is a sine function, right? So I can simply say that I can gather all of this with this, and this should be a sine function. Sorry? I did. It was, so the minus here was supposed to be e to the minus j first, right? This was supposed to be the first, and that second was supposed to be this, right? Look, when you substitute t over 2 substituted here will give you this first, right? Right? And it will give you this, the minus will become plus, and it should be the other side, right? But then, because I got the minus 1 in, so I put the order the other way, okay? So this is equal to 2 over omega, and then sine of what? It's always sine of whatever is up here, okay? So this is sine omega t over 2. Okay. Now, we have seen this before. We have seen sine omega over omega, right? Remember how this function used to look like? That's the final answer. So this is the Fourier transform of that rectangular function. When you have a rectangular function in time domain, you get sine omega over omega. So we call this the sinc function, okay? And remember how it looks like, the sinc function? We encountered this before.
Magnitude 1 at 0.
Yes.
And then,
Yeah, so it looks like this as a function of omega, right? It will look like this, something like this, and then up and down, it keeps decaying, okay? The other way is just symmetric, so. Okay. This is our x of omega as a function of omega. Okay. Now again, we need to kind of look at where is the first zero, second zero, and so on to figure out the locations of those, but that's easy. So whenever this whole argument is a multiple of pi, so pi, 2 pi, 3 pi, 4 pi, and so on, you encounter what? Pi. Sine 0 is equal to what? Sine 0 is equal to what? 0. Okay? Pi. Sine pi is equal to what?
Pi. Omega 0.
Sine pi. Sine 180. Sine 180 is equal to 0, right? Sine 2 pi, 0, and so on, right? So you need to figure out the locations where you will have this whole thing equal to pi, 2 pi, 3 pi, 4 pi, and these are going to be those zeros. Okay? Again, you can figure out this. So omega t over 2 is equal to pi, for example. This will give you an omega equal to 2 pi over t. So this first location is 2 pi over t. And then the next one, 4 pi over t, 6 pi over t, and so on. Right? Okay? When is this, okay, when does this equation have 0 values? Okay? Again, when omega is equal to 0, that's a special case. Because when omega is equal to 0, you have 0 over 0. Right? So that's a special case, and you need to solve that one, and the end result is that it's not going to be 0, it's going to be some value, some amplitude value. Okay? Now, when omega, the other locations where this whole expression is going to be equal to 0, when the sign is equal to 0. Right? When is this sign going to be equal to 0? Whenever whatever is inside the sign is multiples of pi. Sine pi, sine 2 pi, 3 pi, 4 pi, all of these are equal to 0. Any other values for the sine function is not going to give you 0. Right? So the zeros of this occurs when omega omega t over 2, this whole thing is equal to multiples of pi. So m equals 1, m equals 2, and so on. From m equals 1, 2, 3, and so on. Okay? So the first one, for example, is going to be omega t over 2 equals just pi, which is going to give you an omega equal to 2 pi over t. Right? The second one is going to happen when omega t over 2 is equal to 2 pi. This is when m equals 1. This is when m equals 2. Right? And this is going to give you omega equals 4 pi over t. And so on. So now you know those locations, right? The locations of the zeros are just locations of multiples of 2 pi over t. 2 pi over t, 4 pi over t, 6 pi over t, and so on. Okay? Similarly, on the negative side, you have a minus sign. Okay? Anyways, the important thing now is we figured out the expression for the Fourier transform, so how this signal looks like in frequency domain. We were able to do this by calculating the Fourier transform. So this tells me that whenever I have a square function in time domain, the corresponding signal in frequency domain is going to be a sinc function. Okay, this is called the sinc. It's a sinc of omega. Okay, sinc function. And I mean the sinc requires just you have to make sure that this looks exactly the same like this, right? So you have here omega t over 2. Now we need to multiply. So if you want to make this really look like a sinc function, just out of mathematical correctness, so you multiply up there by a t and down by a t, and then you can take the 2 down there, right? And then you have sine omega t over 2, and the result here is going to be t sinc of omega.
Do we have to know this?
Hmm?
Do we have to know the sync function?
You have to?
Do we have to know the sync function?
No, you don't have to. I'm just trying to explain to you when we say a sinc function, it's typically sine x over x. But here we don't really have omega over omega. We have omega multiplied by something over omega. So we need to put it in the right, sorry, it will become sinc omega t over 2, not just sinc omega. Sinc of omega t over 2, okay? But I'm just saying that typically the sinc function, by definition, sinc of x is equal to sine x over x. Some textbooks defines it as sine pi x over pi x. I'm gonna follow the definition just sine x over x without multiplication by pi, okay? Just a definition. This is just what's the meaning of a sinc function, okay? So if you want to really map this into a sinc function, you have to scale things so that whatever is inside here is whatever you divide by. So it becomes, this whole thing becomes a sinc, okay? Anyways, it doesn't matter and it's not really important. You just need, once you get the answer here and you can plot it, that's enough for me. Okay? Plotting it is just simply finding this value. So you substitute omega equals 0 and do L'Hopital, so you can get the value at omega equals 0, and then figure out the locations here. That's more than enough to sketch the segments, right? And that's what you need to do. To do this, you don't really need to do any sinc definition or anything, okay? So square signal resulted into this sinc representation, and curiously, this signal was limited in time. So it actually starts at a particular time and it finishes at a particular time. But when we look at it from a frequency domain perspective, we see that it goes on forever. So it never finishes. It keeps attenuating, but it will never reach 0 until it reaches almost infinity, right? That's a general concept that you have to keep in mind. Any time limited signal is going to be in the frequency domain extending all the way to the infinity, and vice versa. Any time signal that extends all the way to infinity is going to be in the frequency domain limited. You will see that the frequency domain will finish at a certain endpoint, okay? Now, why any time limited signal results in expansion in frequency that causes you to reach even very high frequencies, something like a frequency of infinity value? Because any time limited signal will always encounter a point where the signal will just stop abruptly, right? Even if it is dropping with a slope, it will be a slope, and then there is a point of discontinuity where it will just stop at 0, right? So that abrupt stop means that something in the time domain happened within almost 0 time. So something that happened with very high speed, which means that there is some very high frequency component into that signal. Because of that abrupt stop at some point. That's why any time limited signal will result in a frequency domain representation that goes all the way to infinity, because it will always contain a very high frequency component due to the discontinuity at the point where it just decided to be 0 and stop there, okay? Anyways, the other signal that we were looking at is the delta, shifted delta function. So x2 of t, which looked like this as a function of time at t naught. It's a delta function, so delta of t minus t naught. And we want to see how this signal looks like in frequency domain. So in order to do that, if I want to calculate x2 of omega, I go again to the definition. That's the integration from minus infinity to infinity. x2 of t e to the minus j omega t dt. And then to substitute now, so integration from minus infinity to infinity. x2 is that delta of t minus t naught, and then multiplied by e to the minus j omega t dt. How do you evaluate this integral?
Remove the delta and put t minus t naught.
Yeah, so simply an integration of a delta function, shifted delta function, multiplied by some function of time, right? So that's a delta of time multiplied by a function of time. And then you integrate that, and the integration already here spans the region where the delta exists. The result is going to be simply this function at the location of the delta. So as if you have evaluated this function at the location of the delta, which is going to be what? E to the minus j omega, and then,
Brackets t minus t
no, evaluated at the location.
naught.
Yeah, it's directly T naught. Okay. Again, the property that we learned earlier is integration of delta of t minus t naught multiplied by some function f of t, and you integrate with respect to time from minus infinity to infinity. This is called the sampling property, and the result is going to be simply f at t naught. Right? This was a rule that we studied much earlier, right? Okay. So simply here we have e to the minus j omega t naught. So now again, we were able to see that if we have a delta shifted somewhere in time domain, the result of that is going to be, what is this as a function of omega? As a function of omega, right? It's no longer a function of time because time disappeared. We have t naught, which is a fixed value. It's not a function of time. It's now a function of omega. So what is this as a function of omega? It's a pure phase term, right? It's e to the minus j omega multiplied by some constant. So this is, when you take the magnitude of that, it's constant across any omega. So if you want to plot this in frequency domain, this is our x2 of omega. So if I want to plot the magnitude of x2 of omega, the phase, and the magnitude of x2 of omega, right? So this is the magnitude, and this is the phase diagram as a function of omega. So what's going to be the magnitude? It's constant, equal to 1 at all frequencies, right? Because when you take the magnitude of a pure complex exponential, it will have a magnitude equal to 1, regardless where you are at omega. So the magnitude is a constant value equal to 1 at all frequency component, equal to 1. And the phase term is as a function of omega. Well, how does this look like? Where is your phase? This is the phase, right? This is the phase with the negative, okay? So it's negative t naught omega. As a function of omega, this is what? A straight line with slope equal to negative t naught, right? So it's simply a straight line going through 0. And the slope of that straight line, so tan this angle, if you call this angle theta, okay, tan of that is equal to minus t naught. That's the slope of a line, right? It's tan the angle of the line with the x-axis, right? So it's simply a negative slope line, and the slope is equal to minus t naught. That's the phase of this. So it's a pure phase. It doesn't really introduce any magnitude factor, but it introduces a linear phase given by minus t naught omega, okay? Good. Now, let's go to the next one. Any questions here? No? Okay. Next one was what? x3 of t was e to the j omega naught t, right? This is a pure phase term in time. As a function of time, this is a pure phase term, right? Now we want to get its Fourier transform. Okay, let's apply the same methodology that we worked out before. So x3 of omega is equal to the integration from minus infinity to infinity, x3 of t multiplied by e to the minus j omega t, and you integrate with respect to time, and then the integration from minus infinity to infinity, e to the j omega naught t multiplied by e to the minus j omega t dt. Right? So far, yes, right. Now someone might try to say, okay, I want to make this just one exponential so I can solve the integral, so let's combine the exponentials together. Okay, keep trying. So minus infinity to infinity, e to the j, right? And then I have omega naught minus omega, right? T, correct? And then I integrate with respect to time. Good luck solving this integral. Can you solve the integral? So integrate with respect to time, you will get the exponential again, substitute plus infinity and substitute minus infinity, you cannot get anything. Infinity minus infinity. Right? So I don't know how to solve the integral. It's true. With classical ways or with your mathematical tools that you have studied so far, you didn't study something called complex analysis. Complex analysis allows you to solve these integrals by doing something called contour integral, but you didn't study that. So let's forget about it, okay? It belongs to something in the math called the residue theorem, okay? So we did not study, we don't have that tool. What can we do in this case? Well, we can do something. We can play the game of observation. We noticed in the previous slide, right, that when we had in time domain, so in the previous slide, okay, when we had a time domain signal that looks like this, we ended up with a Fourier transform that looks like this. E to the minus j t naught omega, right? Correct? Was it with a minus or plus? Huh? Sorry? It was with a plus or with a minus?
Minus.
Minus, okay? So we ended up with this, right? Correct? So we started with a delta function and we ended up with a pure phase, but as a function of omega because we were going from time to frequency. Remember when we were going from time to frequency, we performed something very similar to what we did here. It's again, we multiply the function, right? And we multiply by e to the j omega. So this gives you an intuition that when I moved from here to here, right, I had this, which looks like the time domain signal that I'm trying to find its Fourier right now, but I had it in frequency. Okay? But interestingly, since this is the Fourier of this, if I took this one and I applied inverse Fourier to it, what do you expect to get? This. But then if you take this one and apply the Fourier, the inverse Fourier to it, you will see a very similar integral to the one that we were not able to solve here, right? So apply inverse Fourier to this. What do you get? So it's 1 over 2 pi, the integration from minus infinity to infinity. This function, so e to the minus j t naught omega, multiplied by e to the j omega t, and we integrated with respect to omega, right? Okay? Now, look at what will happen here. Don't forget we are integrating with respect, our integration variable is called omega. So what happens when you try to combine these guys?
T and T naught will just be constants.
Yeah, so you will end up with something that looks, so this will become 1 over 2 pi, integration from minus infinity to infinity, e to the j, and then you have inside t minus t naught omega d omega, right? Look at this integral and look at this integral. Okay? There's no difference. I just renamed the integration variable to omega, and I just replaced whatever called here omega naught minus omega. I replaced it here by t minus t naught, and both of these, right, they are not actually my integration variables. My integration variable here is here, and I have e to the j omega multiplied by something. I have here e to the j omega, e to the jt multiplied by something. I integrate with respect to t to minus. So I expect that the solution for this would look like the solution for this. What was the solution for this? A delta, right? So now I expect that the e to the j omega naught t in time domain to produce a delta in the frequency domain.
Really?
Right?
Delta omega, right?
Yes, it's going to be delta as a function of omega, right? And it's going to be, again, when we talked about this, it was this guy that was appearing in my time domain signal delta. So when I look at this, it should be this guy appearing in my frequency domain. So I expect now, by inspection, that if I have, so I expect that this x3 of omega will be some kind of a constant multiplied by a delta of omega minus omega naught. I don't know exactly what's the value of the constant. Okay? But shape-wise, okay, I had complex exponential in time domain. When I looked at the situation that I solved earlier, the delta in time domain produced a complex exponential in frequency, and this gives me an intuition that if I do the opposite, if I put a delta in frequency, it should produce the time domain signal, and then I solve the problem in the inverse way. So now I plug in this delta, so that's, now I do my x3 of t, which is equal to delta of, which is equal to e to the j omega naught t, is supposed to be the inverse Fourier of this thing, right? Since I assume that this is the Fourier transform. So let me solve integration from minus infinity to infinity, a constant multiplied by delta omega minus omega naught. That's the frequency domain function. And then the inverse Fourier is e to the j omega t, and I integrate with respect to omega. Now, if I solve this right side integral, what do I get? 1 over 2 pi here. And then this integration, what does it give me?
E to the power j omega
Yes.
omega naught t.
Yes, exactly. So again, a delta of omega at location omega naught multiplied by a function of omega, and you multiply them and you integrate, then the integral should give you this function at omega equals omega naught, right? So I'm going to get out of this. Again, the constant goes outside, and then e to the j, and then substitute omega naught t. Now for this to be equal to this, what should be the constant?
2 pi.
Exactly. So the constant is going to be 2 pi. And if I know that the constant is 2 pi, I know that x3 of omega is equal to 2 pi delta of omega minus omega naught. So now I figured out that if I have a pure phase term in time domain, the corresponding frequency domain representation is going to be a shifted delta in frequency at the location of the phase term, omega naught, the phase term, right? And it's scaled by 2 pi. So it's no longer just a delta, it's a delta with some multiplicative factor
It's
of 2
fixed,
pi.
right? It's fixed.
It's fixed. What do you mean by fixed?
Like this, we can always use it.
Yes, it's always the case. So whenever you have a phase term like that, the corresponding is going to be
And if it was e to the power negative j omega t.
again. This means that omega plus omega naught, right? So it's always going to be with the correct sign of the omega.
Do
Okay.
we have to know this proof? Do we have to know the proof?
No, it's not a proof. It's just a derivation, and you don't have to know it. I'm just explaining to you where it comes from. Okay. Okay. So we are almost near the end, but I wanted to mention now where do these kind of signals, like the delta signal and the square, appear in? I promised you at the start that we are looking at those shapes or those time functions and their Fourier transform because they appear in systems, right? And when we want to process our signal in frequency domain, we also want our systems to be represented in frequency domain so that the processing can happen in a much easier way. So where these things appear, I'll give you some examples in the next couple of slides. So first of all, for example, the square function, whether it's centered around 0 or shifted or whatever, right, always appears when you want to limit your time domain signal, right? And we have done that before. Okay, so I have this signal that happens from before my life and it continues after my life, right? But I want to process only the last 2 seconds or the last 5 seconds of that signal because I cannot wait forever for the signal to finish. I need to start processing and doing some actions. So you always need to cut part of the signal. And if you want to cut part of the signal, this is only done by multiplying with a square, right? With amplitude equal to 1. And the width, the start and the end of that square is where is your start time and where is your end time, right? So in time domain, typically, if you want to cut part of the signal, you multiply that signal by a square function, by that square function. So again, when we do that in time domain, if we are looking for processing our signal from a frequency domain perspective, we need to figure out 2 things. How does this multiplication in time domain look like in frequency domain as an operation? And then how does the square look like in frequency domain so that I can combine these in frequency domain. So anyways, what we did so far is just looking how to represent this in frequency domain. Okay, that's one thing. What about that delta function? Right, so here, let's call this part okay. What about the shifted delta function? Why do I care about this? Remember what we learned earlier, that if you have some continuous time domain signal and you multiply this signal by a delta at t minus t naught, just multiply. What's going to be the result of this multiplication?
The signal.
Yeah, so if this is called, let's call this y of t, for example, okay, and I have the delta, the result that I will have here is the delta, this is delta of 1, is going to be the delta of t minus t naught multiplied by y at t naught. And we call that the ability to sample of the delta function. So basically, I use the delta function to pick only that value in the equation. And again, if I integrate this, I actually pick the value itself, right? Remember, if I integrate this multiplication, the result of that integration is going to be y of t naught only, without anything, which we used already in the previous slide. So the delta function is always used to sample, okay, continuous signals and convert to discrete. So remember that towards the end of this course, we will learn how you can convert from continuous time signals to discrete signals. And when we do that operation, we will rely a lot on this property of the delta function. We will use the delta function as a sampling function to pick samples from our signal at different time locations. And then we deal only with those samples as a representative of the continuous signal. So we no longer need to deal with an infinite number of values, we can only deal with the ones that we picked, and we call them the discrete representation or the sample version of the signal. Okay? So this is where the delta appears. And again, the phase shift happens whenever you want to perform a delay of a signal. Delaying a signal is equivalent to shifting the phase of that signal positively or negatively. Okay, so the phase shift operation happens. So these are just some examples of where these are used. The other side, or the other part of the story that I wanted to discuss is the fact that in many cases, first, before going into that, I will just discuss something called the duality of time frequency. Okay. So when we looked at the previous examples, we encountered this duality in the last one that we solved. Remember the three cases that we solved for time domain signal that we wanted to get their frequency domain. So we started with the square function, and we found that in the frequency domain, the square function would look like a sinc function, right? Okay. And then we said that if I have a shifted delta, then in frequency domain, this will look like a pure shift term, right? Ej T naught M omega, okay? Minus? Okay. And the next one was if we had e to the j omega naught t, we found that this will give us a delta at omega minus omega naught, right? So interestingly, you can see that I had a delta here. I ended up with a pure phase term. I had a pure phase term in time. I ended up with a delta in frequency. And the same applies to everything. So we can go up there and say, if I had a sinc function in time domain, and I try to look at its Fourier transform, by comparison and by analogy, it will be a square function in frequency domain. Okay? Now, why do I care about this particularly, and why did I do all of this and talk about the duality to discuss this? Because this function, which is a square function in frequency domain, anyone wants to ask anything before I leave this slide? A square function in frequency domain, whether it's a square again centered around zero or shifted, wherever you like it to be, okay, is what we call an ideal filter. Why this is a filter? Going back to the example of your project, right? We said that you need to record your signal, and then you need to look at the frequency domain representation of your signal, which might look like, eventually might look like something like this, okay? Okay. And then we said that if, again, we always assume, again, if you look at actually the spectrum, it never finishes. It keeps on going. If you increase the scale, it will increase with you, okay? So again, practically speaking, we cannot deal with infinite number of frequencies. We'll just say that if the magnitude drops sufficiently compared to the peak value, we cut at that point and we assume that the rest is zero. So we just ignore the remaining part and we finish our signal here. And in this case, we can practically say that this is the bandwidth of my signal. So I no longer have to really look for the theoretical highest frequency, because in this case it can go all the way to infinity. I just look at the highest reasonable frequency with some reasonable amplitude. After that, when the amplitude drops, I assume that this does not exist. Very similar to what we do in time domain when we say that if my signal happened since the start of the Stone Ages, and it continues after my life for another 100 centuries or 1,000 centuries, I only care about a specific time span of the signal, and I don't care about the rest, okay? Or when you discussed in your circuits the transient effect that happens due to switching on the circuit, you assume that after a couple of time constants, it decays enough such that you can assume it's no longer existing, and you are dealing with a steady state signal. You are no longer dealing with transient, because it's already the effect of that became very small. So here also, the signal amplitudes with those higher frequencies is very small, so I ignore those parts and I only consider this as the effective part of the signal, okay? Anyways, this is your voice signal, and then we said we want to divide this into 3 equal bands and deal with each one independently. Now, if I want to extract only one band, if I want to extract, for example, this band only. Exactly. How can I do this? I simply multiply my signal by this filter, right? Now we are dealing with frequency domain representation, so everything is a function of omega. So I multiply those two, and the result of the multiplication is going to be only this part of the signal, right? So only this part of the signal, only this part of the signal. Okay? So this way, you have picked a certain part of your signal around a certain frequency range. You can also pick the second one by multiplying by a square that appears here, and it will have a counterpart in the negative side. Or a square that appears at the higher part and a counterpart. So you pick the third part of the signal and so on, right? This operation of picking a particular frequency range is called filtering. Now, I want you to look at this. When you do this operation in frequency domain, you know that what you did here by multiplying your signal in frequency by this filter is that you picked this particular frequency range of your signal to do something with it, okay? Now try to imagine how this would look like in time domain. This square in time domain is sinc function, right? Okay, and your signal in time domain is this guy, right? Whatever. And then in frequency, the multiplication corresponds in time to convolution. Imagine that we didn't have frequency domain, right? And someone came to you and told you, okay, now to deal with a particular band of your signal, what you need to do is to take this complicated function that goes all the way to infinity and looks like this, and you convert this with this voice, and then believe me, this is gonna get you only the lowest frequency of your signal. You will look at this and say, how come? What's the relation between this, doing this operation, and actually just cutting a particular frequency range? Doesn't make sense. You cannot find it out by looking at the time domain, right? But the only way to understand what you are doing here is to take everything to frequency, including converting the operation. Any convolution in time becomes a multiplication in frequency. And then you look at your band, the signal versus frequency, and you look at what your system is doing, right? Sorry, the system is this one, okay? And your system is actually cutting a particular frequency range. You only understand this by looking from frequency domain. If you don't know about frequency domain, and you discuss only the time domain, the operation looks like a magic, right? I don't know what's happening here, okay? So that's why, in many cases, that's just an example, you actually need that perspective to look at the system and the signal from the frequency domain to understand what am I doing to my signal? What am I doing right now? I'm focusing on a particular part, then I will take that part and amplify it or attenuate it or do whatever using your equalizer. خلاص؟